Welcome back, class. As a reminder, we're on our continuing quest to make a perfect spot-it deck, one which would have 57 cards. Note, again, the printed one only comes with 55 cards, so we want to actually show it's really possible to make one with 57 cards. So, how are we going to do that? Well, we've talked about this idea of making a projective plane that is a way basically to fix up something like R2 and make it so that every pair of lines intersect at a point. The problem being that normally in R2, parallel lines don't intersect at a point. And we've also talked about this whole idea of a finite field, which is basically a finite replacement for R. So I want to start by today talking about the affine plane, which is our equivalent for R2, but for an arbitrary field. So for a field F, this thing that I'll denote A2 of F is the following set of points and lines. Okay, so the points are F cross F, which just if you want to remember, that's the set of X comma Y, where X and Y are in F. And then the lines are going to come in two flavors. We're going to have this LMB line, like before. This is going to be the set of X comma Y, such that Y equals MX plus B. Okay, so these are our lines. This is for each M and each B in F. And then lastly, we have our vertical lines, which I wrote before as L vert comma A. This is the set of points just X comma Y, where X is equal to A. So we have this set of points F cross F that we're thinking about in the plane. Notably, if F is R, then we get exactly the plane we're used to. And then we have a corresponding definition of what the lines are, and we have our usual Y equals MX plus B lines and our vertical lines. But I'm not interested in letting F be the real numbers. I'm interested in what happens if F is, say, the field F7. So let's let F be F7, which remember is just the set 0, 1, 2, 3, 4, 5, 6. So then F squared in this instance, or F cross F, basically my point set, it's the set of X comma Y, where X and Y are in F7. This is now a finite set. In fact, how many elements are in this set? Well, there are 49, right? Because I have 7 choices for X and 7 choices for Y, so there's 49 total points. So this is, to be clear, an analog of R2, except that R2 has infinitely many points, whereas this thing, AF2, it only has 49 points, which is promising if you remember that the points we're talking about are supposed to correspond to some sort of symbols. So these 49 points, they're going to correspond to 49 of our 57 symbols that we're going to need. Then we have our lines. So these are the points. We have our lines. And so we have these LMB sorts of lines. This is the set of all X, Y, where Y equals MX plus B. This is for each M and B in F, so that means there are 49 of these. And then we also have the L vert A. That's the set of x comma y, where x is A. And there are a total of 7 options for A, so there are 7 lines of this type. So remember, the lines here are meant to be our cards. So in some sense, we have here 56 of the 57 cards we want. Now, there are a few problems, but morally speaking, we have this. So I want to write down, just so that we can make sure that we're comfortable with this, I want to write down what one of these lines actually is. So I want to write down, again, we're still in the case that f here is f7, and we're talking about the affine plane over f7. I want to write down this line L, and I'm just going to pick at random L5, 4. What is this? Okay, so this is the set of all pairs x, y, where y is mx plus b. Okay. So if x is 0, what is y? Well, then y is supposed to be 5 times 0 plus 4. So that is to just say it's 4. And then we go on with our lives. What if x is 1? Well, if x is 1, then this is 5 times 1 plus 4. And remember, we're in f7, so 5 plus 4 in f7. Now I have to think in f7 for this line. 5 plus 4 in f7 is 2. So I get 1 comma 2. I'll do one more of these, and then I'll just fill in the rest. For x equals 2, I get y is equal to 5 times 2 plus 4, which would be 14, which is 0 in f7. I'll go ahead and just fill in the rest of these for you. Okay, so here is our line in its entirety. It has, in fact, exactly 7 points on it. And the reason why it has exactly 7 points on it is because there are 7 options for x, and as soon as I pick what I want x to be, I know what y is because of this constraint. So, unlike lines in R2, which have infinitely many points on them, all of our lines have 7 points on them. In fact, actually, if you go and you want to write down L vert 3, that'll work out to be this. And that will also have 7 points on it. So in fact, key observation, every line in A2 F7 has exactly 7 points on it. More generally, you can prove the following proposition. If F is a finite field, then every line in A2F has exactly the number of elements in F points on it. So if your field has, say, 25 elements, then now every line in that affine plane is going to have 25 points on it. So this is all awfully difficult to visualize, because this is not what we normally think of as being a line. Namely, we're used to sort of picturing this whole idea of like a line as just some continuous, smooth curve that doesn't bend, basically is how we're used to thinking of a line. Now, it's not to say I can't graph this, so I'm actually going to pull up for you. Here's a graph. And so I have here a picture for you, f7 squared. This is the same thing, remember, as a2 f7. And I have here one of the lines that I've circled all the points in red. Namely, I circled all the points in red of this line that we just talked about. And so note, again, there's only 49 total points in the plane. They correspond to the 49 ordered pairs of elements of F7. And then each line that we draw corresponds to circling 7 of these points. And that circling of 7 of these points can look pretty random if you just sort of throw it at the page because, well, these points aren't connected in any sort of meaningful way. So, this is what we're talking about, though, is these kinds of lines. And so every line, all 56 of the lines, correspond to some subset of 7 elements out of these 49 elements. You might also notice that if you wanted, you could visualize a vertical line pretty easily. A vertical line really looks vertical, or a horizontal line. Which, by the way, if you've been wondering this whole time why I talked about vertical lines but not horizontal lines, the reason is because horizontal lines are secretly embedded here because the horizontal lines are the ones with m equals 0. The horizontal lines also would really look horizontal. It's just the other lines that end up with this sort of weird thing going on. If you really want to try and make sense of what's happening here, you can think of this as like a torus, where because everything here is happening mod 7, I'm drawing a line here through these points, and then it's wrapping off the top and coming back over here. And so my line here in blue is really the sort of wrapping line, and then my line in red is this similarly wrapping line like that. But that doesn't really super help in terms of interpreting this. And if you imagine instead of 7, we had a much larger number, this picture gets even more chaotic. But what is the thing we actually made this for? So remember, this thing is playing the role of R2 in our projective plane that we talked about before. And so the thing we needed to be true is that if I take two lines that are not parallel, then they intersect in exactly one point. So if F is a field, then any two lines, L1 and L2, with different slopes, intersect in a unique point. Okay, so this is something that over the plane is quite intuitive, because in the plane, if the lines aren't parallel, you can sort of imagine some sort of intermediate value theorem forcing that, hey, these two lines are going to cross each other at some point, and then because the slope of this is positive and the slope of this is negative, as soon as the value of this function is bigger than the value of this function, they can never cross again. So they're forced to cross once because this line of positive slope, say, goes to infinity, and this one of negative slope goes to negative infinity. And so they have to cross, but then they're never going to cross again. So this is very intuitive, and this statement probably doesn't even feel like something that needs a lot of proof over R2. But I want to point out, before we actually talk about why this is true, that this is far, far from obvious when we talk about F7 or any analogous field where we're talking about a finite field, because there's no sort of intermediate value theorem business that says, oh, sort of like these two lines, quote unquote, crossed. Again, remember, if I drew this, I would draw that line that way and this line this way. So they, quote unquote, crossed in between here, but there's no point there for them to cross at. So it's very not obvious that any pair of lines I pick with different slopes are going to intersect. In fact, it's not even really obvious that me using the word slope to describe this m number makes any meaningful sense at all, because, well, this function is not really sort of increasing in a meaningful way. It's hard to exactly make sense of. But at least for this one example, you can notice I picked two random lines and circled them, and indeed these two random lines do intersect at exactly one point. So at least the conclusion of the theorem here that we said is true. in this particular case. But of course, we'd like to think about this in a little bit more generality. Before I actually prove this theorem, though, I want to throw some mud in the water a bit. And I want to show you something where I took, instead of working mod 7, I worked mod 6. Okay, and so remember, you only get a field if you work mod a prime. So here I'm not showing you a counterexample, but I'm just showing you that this question is a little bit subtle. I can still certainly draw lines in z6 squared. So I've just drawn very simple lines here. Here's y equals 2x. Okay, and so 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 0, etc. And I want to point out that two pretty horrible things happen here. Namely, if I take this horizontal line, y equals 4, it actually intersects my line twice. Okay, so 2 is not 1. And if I take the line y equals 1, then it actually intersects it 0 times. So if you're wondering why I made this big deal about fields in the last video, the reason is because if I want this property that every pair of lines with distinct slopes intersect in exactly one point, I need to be working over a field. It is not enough to just work over some ring where I can make sense of lines, because z6 is a ring where I can make sense of lines in z6 squared, but things don't work. So again, the moral here, this is not a field. So why does this work if I have a field? So let's suppose f is a field, and that we have two lines of different slopes. So we have a few cases to consider. Namely, when I say the same slope, I'm including the possibility that both of these lines are vertical. But remember that our official definition of what it means to be vertical is different than for any other line. So I technically have to include the case, well, what if one of my two lines is vertical? They can't both be vertical, because two vertical lines are definitely not going to intersect. But if one of them is vertical, well, then I take the point x equals a, and I plug it in for x here. I plug in a, and then y is equal to m times a plus b. That works. So the interesting case is the case where neither line is vertical. So that's the case we're going to focus on. So I'm going to let L1 be given by y equals m1x plus b1, and L2 be given by y equals m2x plus b2. And I want to show you that these two lines intersect, using only the fact that all these things are happening in a field. So I want to solve the equation, really the system of equations, y equals m1x plus b1, and y equals m2x plus b2. And I want to solve this system of equations in the field F. So I have to think pretty carefully if I want to make super sure I don't cheat at all. And if I want to make super sure I don't cheat at all, I really have to make sure at every step I come back to this sheet and refer to the axioms of a field. I'm going to be very specific about where one of these axioms comes up. Namely, we're going to be very careful to be mindful when the fact that there's inverses shows up, because that's really the thing that sets apart F7 from Z mod 6Z, is that every element has an inverse. But if we have y is equal to m1x plus b1 and y is equal to m2x plus b2, then we'll get m1x plus b1 is equal to m2x plus b2. Okay, I haven't used any field axioms here. I've just said that, hey, if two things are equal to the same thing, then they're equal. That had better be true. I'm now going to use the existence of additive inverses to move things around so that I have all my b's on this side and all of my mx's on this side. So I'll get m1x minus m2x is equal to b2 minus b1. And now I'm going to factor out the x using the distributive property that we have previously stated. To b2 minus b1. And now remember what it is we assumed about these lines. We assumed they have different slopes. So the fact that these things have different slopes is exactly saying that m1 is not equal to m2. Which means that m1 minus m2 is not equal to 0. And if you want to look back at our list of axioms, what we've said is there's this unary operation multiplicative inverse with the property that every non-zero element has some number you can multiply it by to get 1. In other words, if you want, we can divide by non-zero numbers, is what this says. So in particular, this m1 minus m2, this is a non-zero number, so we can divide by it, which gives us x is b2 minus b1 over m1 minus m2. And so as soon as x is this, then I know what y is. Y has to be, remember we're on both of these lines, so y has to be m1x plus b1. So y is m1 times b2 minus b1 divided by m1 minus m2 plus b1. And this is, we've shown, the only point that might be on the intersection between these two lines. So what we've shown so far is that there is at most one point x comma y where these two lines intersect. And in particular, what was our logic here? If you read through and spell out all the logic of what's happened so far, we've said, okay, suppose both of these things are true, that y is m1x plus b1 and y is m2x plus b2. That is, suppose we have a point that is on both lines. Well, then these two things are equal, and so you can do some algebra, and so then x has to be this thing, y has to be this thing, and so if there's any point at all that's on both of these, it's this point. And so in particular, so far, we've proven that this thing between the red and green lines does not happen. Namely, it's not possible, if we're working over a field, for there to be a line that intersects another line in 2 points. And again, the thing about our proof here that would not have worked if we really were thinking about z mod 6z is that we would not have been able to take an inverse of the difference of the slopes. So in this case, that difference of the slopes would have been 2, and you can check 2 has no inverse in z mod 6z. If you take abstract algebra or number theory or something, you'll learn that's because 2 and 6 are not relatively prime. That's what really sort of broke that example. What remains to check is that there actually is a point on the intersection. And, well, fortunately, I have a pretty good guess as to what point I should try. Namely, I should probably try to make sure that this point is really on the intersection. So certainly, this point is by construction on the first line, but I've got to check that this point, xy, is really on the second one. So this is just going to be checking that if I take m2 times b2 minus b1 divided by m1 minus m2, and I add to that b2, I need to check that I really get the same y. That is, I really get this thing. I'll just go on algebra autopilot here. Okay, so that went by really fast. It's not super important that you pay close attention. You might notice there was some algebra trickery in the middle where we had to add and subtract the same thing out of nowhere so that stuff factored. But what's the moral of the story here? The moral of the story is I have shown you that if you plug this x into the first line, you get that y. If you plug this x into the second line, you get that y, but then you do all of this nonsense, and then you get that, which is exactly the same thing as that. And so in particular, what I've shown is that if x, y is this thing b2 minus b1 over m1 minus m2, comma m1 times b2 minus b1 over m1 minus m2 plus b1. If xy is this, then the intersection between L1 and L2 is exactly that point. I'm going to call this x naught, y naught. Is exactly the set x naught, y naught. So in fact, they intersect at a unique point, as I would hope. Okay, so what we've just constructed is the affine plane over a field. So that is our analog of R2. But of course, the thing we wanted for our spot-it deck wasn't the analog of R2, it was the analog of R2 after we threw in all of these extra points. So next time, we're going to construct the projective plane over an arbitrary field, and then we'll finally have our spot-it deck. Until next time, be well.